Hello and welcome to The Explainer. Today we are digging into one of the most fundamental rules in the entire universe. It's a law that governs everything from your morning routine to the final fate of the cosmos. As you'll see, it's a game you can't win, you can't tie, and you can't even leave. So let's get right into it.
It all starts with a really simple, everyday question. You pour a hot cup of coffee, and what happens? It always gets cold. Always. But have you ever seen the reverse? Have you ever walked into a room and found your iced coffee has magically heated itself up? Of course not. And that's not just some weird quirk, you know? It's a huge clue that points to a very deep law of physics.
To figure this out, we're not actually going to start out in the cosmos. We're going to start right here on Earth, with one of humanity's greatest inventions, the engine. For centuries, we've been chasing this dream of a perfect machine. But as we're about to find out, the universe has some very strict rules about that.
Okay, so the star of our story is the heat engine, or machina thermica, as it's called in the source material. This thing is the beating heart of our world. It's in our cars, our power plants, everywhere. And its job sounds simple enough. Take heat and turn it into useful motion. Turn heat into work.
Every single heat engine, no matter how simple or how complicated, runs on this exact same three-step cycle. First, it sucks up heat from something hot, like burning gasoline. Second, it uses a chunk of that heat to do work, like pushing the pistons in your car. And third, and this is the part that really matters for our story, it has to dump the leftover heat somewhere colder, like into the air around it. That third step is the key.
So, how good are we at this process? Well, a typical internal combustion engine, like the one in your car, is only about 30% efficient. Let that sink in. That means for every gallon of gas you burn, about 70% of its energy is just lost, pushed out into the world as useless waste heat.
And that leads to the billion-dollar question that inventors have been asking for ages. Why? Why all that waste? Is it just that our engineering isn't good enough? Couldn't we just be a little bit smarter, a little more clever, and build an engine that's 100% efficient, one that turns every single bit of heat into useful work, with zero waste?
Well, the search for that perfect engine takes us out of the garage and into the world of fundamental physics. Because it turns out the problem isn't with our blueprints. The problem is with the universe itself.
And this is the absolute crucial takeaway. The inefficiency of our engines isn't a bug that we can eventually fix. It's a feature. It's a non-negotiable law of the cosmos. We're not failing to build a perfect engine. We literally can't, because the universe forbids it. The name of that law? The second law of thermodynamics.
Now, this law has a couple of famous ways of being stated by two physicists, Kelvin and Clausius. And at first, they sound totally different, but they're really just two sides of the same coin. Kelvin's statement gets right to our engine problem. A perfect, 100% efficient engine is impossible. Clausius's statement explains our coffee problem. Heat just doesn't flow from cold to hot on its own.
And here's the rule, straight from Lord Kelvin himself. It's a total brick wall. What it's saying is, you can't just take a bucket of heat from one place and turn all of it into work. It's impossible. The universe demands a tax. You must waste some of that energy. You have to dump some of that heat into a colder place.
And this law, this one rule, is what completely demolishes the dream of moto perpetuo, or perpetual motion. Specifically, what's called a perpetual motion machine of the second kind, a machine that could just suck heat out of the air around it and run forever. It's a brilliant idea, but the second law says, nope, not happening. Ever.
Okay, so 100% is off the table. We get it, the universe says no. But that just leads to the next obvious question, right? What is the limit then? If we can't get a perfect score, what's the highest possible grade the universe will actually let us have?
And the answer comes from a French engineer named Sadi Carnot. He imagined a completely perfect, totally idealized engine, a theoretical benchmark. And his big insight, the Théorème de Carnot, says that no real-world engine can ever be more efficient than his ideal one. The Carnot limit is the ultimate speed limit for turning heat into work. It's the best anyone can ever hope to do.
But still, why? Why is this a rule at all? It feels like we're just saying, because the rules say so. What is the universe actually enforcing here?
What's going on under the hood, on a microscopic level, that makes this law so unbreakable? Well, the answer has a name, and it's one of the most profound and, frankly, most misunderstood concepts in all of science. We have to talk about entropy. This is the hidden code that writes the rules of chaos. So what is entropy? People usually just say it's a measure of disorder, but let's go a little deeper. At its core, entropy is simply about counting possibilities. It's the number of different ways you can arrange all the tiny particles in a system without changing how it looks on the outside. The more ways you can arrange it, the higher its entropy.
To really get this, we need to separate two ideas, the macro state and the micro state. The macro state is the big picture that we see, like the coffee is hot. The micro state is the nitty-gritty detail, the exact position and velocity of every single molecule. And here's the mind-blowing part. For one single macro state, there can be trillions upon trillions of possible microstates.
Let's use an analogy. Think of a brand new deck of cards right out of the box. It's perfectly ordered, sorted by suit, then by number. How many ways can the deck be in that one perfect order? Just one. That's it. That's a very low entropy state. There are very few ways to arrange it. Now, take that same deck and give it a really good shuffle. The cards are all mixed up. It's chaotic. But how many ways can the cards be mixed up? Billions? Trillions? Almost any random arrangement of cards counts as shuffled. This is a high entropy state. There are a massive number of possible arrangements. And here it is. This is the big secret. The second law of thermodynamics isn't some mysterious force. It's just probability. It's just statistics. There are so many more ways for things to be disordered than for them to be ordered. So over time, systems just naturally wander into the most probable states, the ones with the most arrangements, the ones with the highest entropy. The physicist Ludwig Boltzmann was the one who put this all together. He showed that the total entropy of an isolated system, like, say, the entire universe, can never go down. It only ever goes up. And this relentless, one-way march from order to disorder is what gives time its direction. It's why we see glasses break but never unbreak. It is the arrow of time. So this leaves us with one final, pretty heavy question. If the universe as a whole is always getting more disordered, always moving from a state of low entropy to high entropy, what's the end game? What is the ultimate fate of a cosmos that is constantly and irreversibly running down? That's the thought I'll leave you with.